In today's lesson, we're going to be looking at proof by contradiction. This is something that can actually be really fun, but also a little bit weird. Sometimes we can't prove something directly, so we're just looking at this part here. We can do something that's actually pretty cool. And sometimes some people think it's a little bit counterintuitive, but we can do something called reductio ad absurdum. Now, I'm not an expert at Latin by any stretch of the imagination. In fact, I would say I know close to zero. But that sentence makes me think of reducing something until it's absurd. And that's actually a really good description of proof by contradiction. So, we're going to be looking at some things that we cannot prove directly, and we're going to use proof by contradiction instead. The recipe to do this is, we're going to assume that what we're actually trying to prove is false. We're going to show that if you work logically from this assumption, you're going to produce something mathematically silly. You're going to produce a mathematical contradiction. And I like to call this step, do stuff until it breaks. Then we're going to conclude that we were wrong to assume the statement is false. And then we're going to conclude that the statement we're trying to prove must actually have been true. So, here's the first proof by contradiction that we're going to do. We're going to show that the sum of two positive numbers is always positive. So, the opposite of this would be the sum of two positive numbers being negative. So that's going to be what we're going to work on with this. So, let's get our proof going. We need to have two positive numbers. So A is going to be a positive number, and so is B. And we could write them as an element of the positive real numbers. Now, we want to assume the opposite of what we're trying to prove. We're trying to prove that if we add these two positive numbers together, we're going to get a positive result. So we can't just do that by going, well, of course it is, or 1 plus 2, they're both positive, it's going to be 3. It's just common sense. We're going to assume the opposite. So we're going to say, okay, well, if we add A and B, let's assume we're going to get a negative result. So that means A plus B will be less than 0. I like to put assume above the thing that we're assuming to be true, the opposite of what we were looking at. So, now we're going to do stuff. With this step here, we could take B away from both sides. So we could have A is less than negative B. Whether you realize it or not, we've actually got a contradiction here. We said before that A was a positive number. So negative B must be a negative number. But it doesn't make sense to say a positive number is less than a negative number here. So that's our contradiction. So let's write contradiction. We can't have a positive number A being less than a negative number, which is negative B. So therefore, A plus B must always be positive. Okay, so it's a little bit strange, but let's see if you enjoy that one. Now, this one's actually kind of tricky, so we'll come back to this one in just a moment. Let's have a look at another, on the easier side example. So we want to show that we've got a sequence of numbers A, B, and C. We want to say if they're a Pythagorean triple. Hopefully when you think that, you're thinking of your friends 3, 4, 5, and all the other Pythagorean triples that of course you have all memorized off by heart. Just kidding. We want to show that A, B, and C cannot all be odd numbers. Well, in order to do that, let's assume the opposite. Let's assume A, B, and C are all odd. Now, there's lots of different ways of doing this proof. I think this is the simplest way of demonstrating what we want to show. So, hopefully when you saw Pythagoras, you immediately thought A squared plus B squared equals C squared. That's going to be the way that we look at our proof here. So we've got A, B, and C. If A is odd, then it follows that A squared is odd. And we're able to say this because in a previous proof, so previously showed that an odd times an odd equals an odd. We did that in a previous lesson. So therefore, b squared and c squared also odd. Okay, so let's have another look at that. A squared plus b squared is on the left-hand side of our equation. That's an odd plus an odd, which we previously showed was even. So that was in a previous proof. Now, whether you realise it or not, we've reached our contradiction. A squared plus b squared equals c squared. We said that a squared plus b squared, an odd plus an odd, was even. But the problem is, an even cannot equal an odd, because we said c squared was odd. So because an even cannot equal an odd, that's our contradiction. So that's our contradiction. I'm just going to write contradiction. Therefore, A, B, and C cannot all be odd. So can you see, by assuming the opposite, so what we were trying to prove is that they cannot all be odd numbers. So the opposite of that was, well, they can all be odd numbers. We did that, and then we examined what we had, and by using a very simple property that we've looked at in a previous lesson, evens and odds, we showed that an even number cannot equal an odd number, therefore this cannot be true. The next proof is one of my favourite proofs by contradiction because it relies on something that seems sort of not that important or a little bit obscure. We want to prove that the square root of 2 is not a rational number. That means it's an irrational number. And that means that root 2 cannot be written as a fraction. And we said that fraction could be a over b, where a and b are elements of the integers. It is important to remember that b cannot equal 0 here because it's on the bottom of our fraction. Now, just thinking back to when we talked about rational numbers, we also talked about the fact that a and b cannot have any common factors. So that was something really important about rational numbers we've previously looked at. So, assume the opposite. We're going to assume, so here's our assume step, square root 2 is rational. I nearly wrote irrational then, is rational. So therefore, the square root of 2, if it's rational, we can say that's equal to a over b. Now, this proof follows a little bit of a recipe, and because I know where we're going with this proof, I'm able to show it to you. And you might be like, oh, why is that step happening? All I want at the moment is for you to understand whether it's true or whether it's possible to go from one step to the other. So I want you after each step to think to yourself, is that true? Does that work? Can I see how that happened? I know where we alternately need to end up, and hopefully if you follow the same recipe, you'll be able to show that the square root of 3 is irrational. But it is kind of a proof at this level that it's nice to see first. I hope that made sense. So, do you agree that it would be okay if we squared both sides? Well, if we squared both sides, we would get 2 equals a squared over b squared. So again, I just want you to be like, okay, do I understand how we got from that step to that step? Yep, all we did was square both sides. Now what I could do is I could multiply both sides by b. So we could say 2b squared equals a squared. Well, that's interesting. That's saying that a squared is 2 times whatever b squared is. So that means a squared has to therefore be even. So we're going to write a squared is even. Now, due to a previous proof, that means therefore a is even. And we've proved that previously. Okay, so if a is even, that means a can be written as 2 times a number. In our direct proof thing, we said an even number is just 2 times another number. And because we've introduced k, let's just specify that k's got to be an integer. So a can be written as 2 times a number. So again, I just want you to say, ask yourself in your head, do you understand how we went from each step to the other? You don't need to know where we're necessarily going, but I need you to understand how we go from each step to the next. Okay, so let's continue. I'm going to go over here. If a equals 2k, then we can sub that back into 1. So we're going to write sub into 1. It doesn't matter what the value of k is, remember. We're just saying a is an even number, so it's 2 times another number. Any even number can be written in that form. If a was equal to 42, k would be equal to 21. Doesn't matter. We're just saying that's our general way of writing an even number. So let's sub that back into 1. We're going to get 2b squared equals, and what was a? 2k, but all of that squared. So that means 2b squared is going to be equal to 4k squared. So hopefully you're again thinking, how do we go from one step to the next? And you're feeling comfortable. Okay, let's divide both sides by 2. So b squared equals 2k squared. Oh, well, that's interesting. That means that b squared is even, because b squared can be written as 2 times something. And if b squared is even, that means therefore b is even. Now hopefully you've seen that step and now you're intrigued or excited and see that we've formed a contradiction. And it's a little bit of an obscure one at first. We said in this line here that a is even, and we subsequently found in this line here that b is even. That causes a problem. We said when we defined the rational numbers that a and b did not have any common factors. That was the rule for a number to be rational. It can be written in a simplest fractional form. So let's make a comment about that. A and b cannot have common factors, because if they're both even, hopefully you can see that they'd both have a common factor of 2 at a bare minimum. Maybe 2, 4, 6, 8, something like that. But bare minimum, if they're both even, they must both have a factor of 2. So therefore, that's our contradiction. It's a bit of a weird step, but this is the contradiction step. I'm just going to write contra, because I can't be bothered writing contradiction. So because a and b cannot have common factors, because we said that was the definition of a rational number, it can be written in a simplest fractional form, that was our contradiction. Our contradiction means that our assumption that we said at the start cannot be true. So therefore, root 2 is irrational. That one's a little bit weird, and some people can get really upset thinking that this step here that we talked about is not a contradiction. It's a little trickier. But remember, go back to that definition of a rational number and really think about that carefully. I want you to go ahead and prove that root 3 is irrational yourself. There's a link on the portal, so I'm going to write link. That if you really struggle to do it yourself, there will be a video that goes through how to do that. But I'll give you a hint, it's very similar to this proof here, but rather than thinking of evenness, think about factors. So here we said a is even, a squared is even, therefore a is even. Think of it instead as a squared has a factor of 2, so a has a factor of 2. And if you think of it like that, that will be helpful when you're looking at the square root of 3 rather than the square root of 2. Okay, this one is a similar proof, and if you're familiar with logs, I think you might find this one quite nice, and you might like to give this a go yourselves. If you're not familiar with logs, just keep following on. So we want to do a similar proof. We want to prove that this is irrational. So we're going to assume that log 2 of 7 is rational. So that means that log 2 of 7 could be written as a fraction, a over b. Pen's having a bit of trouble. And that would mean that a and b are an element of the integers. But technically b can't be equal to 0. So perhaps if you wanted to be a bit more specific with that, you could say a is an element of the integers and b is an element of the integers, but take away 0 as an element. Okay, so we've got log 2 of 7 equals a over b. Remember, logs are a question. They're basically saying 2 to the power of what equals 7? Or 2 to this power equals 7. So 2a over b equals 7. If you're not familiar with this step, please let me know and I'll go through logs with you. If we raise both sides to the power of b, I'm going to write an extra step here that you don't have to, but you could write 2 over b to the power of b equals 7 to the power of b. Hopefully you can see on this side, we'll be left with 2, and these b's cancel, a equals 7b. Now, this is a problem. This side, we have something that's always going to be even. 2 raised to any power is going to be something that's even. Is that true of the other side? Well, no. We said an odd times an odd is always an odd. So 7 raised to a power is always going to be an odd. And we've got a familiar situation here. An even cannot equal an odd. That's our contradiction. And our contradiction says that our original assumption must not have been true. And our original assumption was, assume that log 7 is rational. So we can write, therefore, log 2 of 7 is irrational. The last and possibly trickiest proof we're going to do is that there are infinitely many prime numbers. Hopefully you're able to see what our assumption will be based on the previous questions that we've done. We're going to assume that there are a finite number of prime numbers. So assume a finite number, that's my shortening for number, a finite number of primes. So, if there are a finite number of primes, that must mean that there is a biggest prime. And biggest is in quotation marks, because we know that's not actually true. There are an infinite number of prime numbers, but we're assuming the opposite, a finite number. And if there's a finite number, one's got to be the final and largest number. So, let's just say we wrote out a list of our finite number of prime numbers. So we're going to write the primes are, so we're going to write P1, lowercase p1, to represent our first prime number. P2 would be our second prime number, and P3 would be our third. And we could keep writing our list until we finally got to the second last prime number, which we could write as Pn minus 1. And the final prime number would be Pn. So that's our last prime. So Pn, n would be the number, how do I explain that? Just like we had P1 was the first, P2 was the second, P3 was the last, Pn, whatever that number n is, represents the last number in the list, the location of the last number in the list. There we go. And n would represent the number of prime numbers. So n minus 1 just represents the number before Pn, so the second largest prime. This proof gets a little bit weird now. Let's just say we decided to multiply all of these primes together. So we've multiplied all of our primes together, P1 times P2 times P3, going all the way up to Pn minus 1 times Pn. And because we're going to be using this later on, let's call that 1. Now let's write out this number again, but we're going to add 1 to it. So we have created a new number here. We've got P1 times P2 times P3 going all the way up to multiplied by Pn minus 1 times Pn plus 1. Now, if we decided we were going to do a little bit of a calculation here, we wanted to do number 2 divided by number 1. Well, there's two things that could occur here. Well, actually, no, let's step back a bit. Hopefully you can see if we did equation 2 divided by equation 1, we're going to get something with a remainder of 1. And we'll go on the side of our page just to talk about that for a moment. Just say you had a number 2 times 3 times 5 times 7. So just pretend for a moment that that's our total list of prime numbers. We would get 210 for this. But just say we took 2 times 3 times 5 times 7 and we added 1 to that, we would get 210. Now, if we take 210 plus 1, which is 211, if we wrote that 211, so the prime number list we had, plus 1, and we divided that by 210, and I'm just going to change that to a mixed number so you can sort of see what we're doing there, we would have a remainder of 1, which we would put over 210. So that's the situation that we've got here. We took our list of primes, that list of primes we added 1, and if we did 211 divided by 210, we would have a remainder of 1. I know we don't really talk about remainders these days in sophisticated maths, but it's really important for this proof here. So that number has a remainder of 1. There are 2 possibilities of what could happen here. Case 1. That number that we created is not divisible by any of the previous primes. So that's true of either of our cases. So let's write that just up here. Number created not divisible by any previous primes. So, case number 1, that would mean that perhaps our number is a prime. If our new number is a prime, that's a problem, because our new number that we've created by multiplying all of these primes together and then adding 1 has to be bigger than Pn. But we said Pn was our biggest and last prime. So that is a contradiction. Because our number, and that was 2, so 2 is greater than Pn. That's the contradiction we've got here. Now there's a second possibility of what could be going on here. Perhaps our new number is a composite number, so not a prime, but it has a factor, which is a prime number, which is larger than Pn. This would again be a contradiction because we said that Pn was our largest prime. But if there's a number, which is our number which we created in 2, that all of the primes multiplied together plus 1, we said if that number, a composite, is a composite, then it must have prime factors. But those prime factors were not included in that list we had already, so it must be a number larger than Pn. But we said Pn was the largest, so contradiction. So we can conclude with, therefore, there are infinitely many primes. A little bit of a strange proof, that last proof, but I hope that you can look at each step and understand what was going on there. I would like you now to, for homework, complete the exercise 8C questions as listed at the front of this document.